In our study of the integers, two things that we looked at a little bit in depth were the fact that integers could be factored into products of primes, and we looked at the idea of the greatest common divisor of two integers. So we want to think about these ideas, which were pretty powerful in the integers, and turn them into something a little more general that might work in other settings. And so in order to talk about this, primes and divisors, we need to have an idea of multiplication in whatever set we're going to talk about. So we're going to think about one set of things that are very useful, which is polynomials. So we're going to think about the set of all polynomials. I have an idea of multiplying in polynomials. I can multiply two polynomials together and I get a polynomial. And so that lets me also talk about factoring. So for example, if I have the polynomial x squared plus 5x equals 6, I know that I can factor it as x plus 2 times x plus 3. And so one big question is, so that is the way I'm going to factor this. Are these what I want to think of as primes? What do I mean by prime? It certainly seems like x plus 2 that I can't factor that more, but what explicitly do I mean by that? So as an example of where we get into trouble and where we need to know what we're talking about, if I think about something like, I want that to be a minus, not a plus, something like x squared minus 2, I can factor that as x plus root 2 and x minus root 2. And so again, I want to know, are those primes? Are those things that I want to consider as factors? And do I want to talk about that as the factorization of this? And one way to see why this is a little complicated is that I could take like the number 2, which we think of as prime, which means its only factors are 1 and itself, but I could write that as 1/2 times 4. Or I could write that, like in this example, as root 2 times root 2, and we don't really think of those as factorizations, right? So what do we mean by a factorization is something that we know in the integers, but we need to talk about in terms of polynomials. Another example, if I do something like x squared plus 1, we kind of want to say, no, I can't factor that, but I can. I can write that as x plus I times x minus I, where I is the square root of -1, right? So this is something that does factor if I allow complex numbers. If I don't, then maybe it's something that I would want to talk about as prime. So our big question is, what do we mean by prime? All right, so we want to take the ideas that worked in the integers and generalize them to something like polynomials. So if we think about the integers, there are two things that we can do in them. We can add integers and we get another integer. We can multiply integers and we get another integer. A couple of notes on that. Addition in the integers, we might also want to think about subtraction, but subtraction really kind of is an outgrowth of addition. Subtraction is adding negatives, right? It's adding the additive inverses of integers. So subtraction really is just addition, but with negative integers. Multiplication is nice in the integers. Division is not. So there are some ways in which division is fine and is just like subtraction. It's adding inverses. Sorry, it's multiplying inverses. But it's not always okay, because, so for example, I can do 4 divided by 2 is 2. That's fine, and it's an outgrowth of multiplication, right? This is like 4 times the inverse of 2. But 3 divided by 2, that gives me 1.5, which is not an element of z. 1.5 is not an integer. And so multiplication is good, division is not always so good. Addition is fine, and subtraction, just adding inverses, is fine. But division we're going to have to always be a little bit careful of. So we want to think about, are there sets that are like the integers? Are there sets that also have addition and multiplication? So here's our first step toward setting up these rules to find other sets that are like the integers in this way. So here's our definition. For a set S, a binary operation on S is a function whose input is 2 elements of S and whose output is 1 element of S. So the mathematical notation for that is written here. The S cross S here, all that's really talking about is that the input for our function is ordered pairs of elements from S. Okay, that's what the S cross S notation is talking about. And then the output, notice, is in S also. Okay, so some examples. Addition on Z is a binary operation. It's a function, and the function of addition we usually give this notation, the little plus. It's a function from pairs of integers to integers. Okay, so for example, I could write the plus function of the pair 3, 2 is equal to 5. If I plug 3, 2 into my plus machine, I get 5 out. This notation gets a little cumbersome, so usually the way we write it is 3 plus 2 equals 5, right? We don't use that sort of function plug in 3 plus 2 notation. We just write 3 plus 2. Multiplication is similar. So I have this multiplication function. I'll use the dot for it. It goes again from Z cross Z to Z. And I might write multiplication of 3, 2 is 6. But really, again, the way we typically write it is just 3 times 2 equals 6. But still, the function is give me 2 integers, I will give you another integer as my output. Division does not work that way. So this is kind of what we were talking about a little bit ago. Division sometimes is fine, but sometimes is not. So 3 divided by 2 is not an integer. And so the output is not in the right set. So if you remember, our definition said you have to go from a pair of things in S to S, and that's not happening here. 3 divided by 2 is not an integer anymore. It's tempting to say, well, what about, is division a binary operation on the rationals? Because if I divide 2 rationals, I get a rational number. So 3 divided by 2 is 3/2, which is a rational number. But division also has a problem with 0. So I cannot divide by 0, which means for this binary operation definition, for division, not only is the output sometimes an issue, like that 1.5, it's not an integer, which we want it to be, but also the input isn't always everything. The domain of the function is not good for division because of 0. So 0 is not in the domain, so it's not really a function from the rationals to the rationals either. All right, so we're going to think about this definition, these examples, with our set of polynomials again, okay? So for polynomials, addition is fine also. I can add 2 polynomials. So let's say x plus 2 plus x squared plus 3. What I get out of that is a polynomial. It's the polynomial x squared plus x plus 5, right? So addition is a binary operation on the set of polynomials. I can add 2 polynomials to get a polynomial. So this is a good binary operation. Multiplication is similar. I can take 2 polynomials, and this works for any 2. I'm just picking one example to do. And my product will be a polynomial. So in this case, it's x cubed plus 2x squared plus 3x plus 6. So I can take two polynomials and add them and get a polynomial. I can take two polynomials and multiply them and get a polynomial. But again, division is a problem. If I wanted to do x squared plus 3 divided by x plus 2, or if we write it as a fraction like this is not a polynomial anymore because of that x in the denominator. Like in the integers, sometimes this might work out. If x squared plus 3 factored and had an x plus 2 term, we might be able to cancel those x plus 2's and end up with a polynomial, but most of the time this isn't going to work the way we want it to. So it turns out so far the polynomials are acting a lot like the integers in these specific ways. So next we're going to think a little bit more about what are the properties of addition and multiplication in the integers, and do they still work with something like polynomials.